Hi there, this is 10 multiple choice questions on optics. So I will put the questions on, you can have a go at them, then I'll give you the answers, and then I'll do a full walkthrough explanation of every single question. So start with the questions. Each one will be on, like 3 seconds, so just pause it or rewind it if you miss it. Then I'll put the answers on, then we'll go for the answers. So now the walkthrough will begin. So first question, a ray of light incident on a glass air boundary of a rectangular block as shown. And it gives us refractive index of the glass, 1.5, refractive index of air is 1. The angle of incidence for the glass air boundary is 44, so that is 44 degrees. And the question wants us to identify what path the ray of light will take. So before that, we need to calculate the critical angle. So the critical angle comes from Snell's law. So Snell's law is kind of the bread and butter of optics. So it's n1 sine theta 1 is equal to n2 sine theta 2. At the critical angle, what you need to remember is that when it hits the boundary at the critical angle, it refracts across the boundary at 90 degrees. So the angle of refraction is 90 degrees. So knowing that, we've got m1 sine theta c, because the first angle is the critical angle, is equal to n2 sine 90. Sine 90 in your calculator is 1, so it's just equal to n2. So that means that the critical angle, or sine theta c, is equal to n2 over n1. Now, what's something you might be taught at school, or incorrectly out of a book, for example, would be that this equation is sine theta c is 1 over n. Which is fine, it works sometimes if the second material, N2, is air. So obviously the 1 would work. But if you have two different materials that are connected and one of them's not air, then it won't work. So it's an issue. So the actual equation is the one in the bottom left. Okay, just in case you didn't know. So let's go back to the question. And well, actually before then, you've got to remember that if the angle of incidence is greater than the critical angle, you'll get total internal reflection. And if it's less than the critical angle, less than theta c, it refracts out into the other medium. So you just get refraction. So in this instance, the refractive index of the glass is 1.5, the refractive index of air is 1. So what we need to do is establish whether this is greater than or less than the critical angle. So the equation sine theta c is equal to n2 over n1. So the critical angle is inverse sine n2 over n1. n2 in this instance is the air, so that's 1 divided by the first refractive index, 1.5. That calculated is 41.8 degrees. So the 44 degrees is greater than the critical angle, so it will experience total internal reflection. So we'll come in, reflect. Because it's a square, this angle here would also be 46 degrees. Well, we've got 44 degrees incident angle. The angle of reflection would also be 44 degrees, and then we've got a triangle. So obviously that's 90 degrees, then it's just angles make it up to 180. So that angle will be 46 degrees, which again is greater than the critical angle of 41.8. So you'd get total internal reflection yet again. So the path would be in from A to B, and then from B down to D. So path D. So there's quite a lot in that one. Some people have found that straightforward and others might have struggled. Let's look at question 2 then. So this one gives us 2 different optical fibres. One's a bit wider than the other, and they are both the same length L. So let's look at the possible answers. So the first one is n over c sine theta, and essentially the horizontal speeds in both cases are basically the same. So logically, if the speeds are the same horizontally, then it's just going to be the same expression. So the answer is simply A. Let's look at the next one. This one's relatively straightforward as well. So an electromagnetic wave enters a fibre optic cable from air. On entering the cable, the wave slows down to 3/5 of its original speed. What is the refractive index? So refractive index can be given as the ratio of the wave speed. So the speed of light divided in the first substance, which is the speed of light, divided by the speed of light in the substance. So the refractive index will be the speed of light in the substance, which we can just call C, divided by, and then it's 3/5 of its original speed, so it's 3/5 of C. So the C's cancel, bring the 5 up, so the refractive index is 5 over 3, and 5 over 3 approximates to rounds to 1.67. So the answer for this one is D. So look at number 4. So this one's similar to the one that we did a couple of questions ago, I think the first one. So what we have to do is, it gives us four answers. We've got to pick one as to which path it follows. What we've got though, we've got the refractive index of the prism, which is 1.5. And we also know the refractive index of air is 1. So we can actually figure out the critical angle straight away. So critical angle would be sine theta c. It's equal to n2 over m1, as described earlier in question 1. So theta c is equal to inverse sine. By the way, if you got question 1 right and this wrong, you might want to go back and look at the explanation for question 1. So n2, it's in air, so that's 1 divided by the refractive index of material 1, which is the glass at 1.5. So that gives us a critical angle, which is equal to 41.8 degrees. It's the exact same as the other question. So then we just need to figure out which. So we know it's 41.8 degrees. So the angle of incidence is, just like that. Angle of incidence is what, 45 degrees. So that means it will hit this one at 45 degrees, which is above the critical angle. So we're going to get some total internal reflection. Let's just look at our options for our answers. So it will reflect, by the way, up in this direction. So as you can see from our available answers, the only one that it could possibly be is D. It's the only one that undertakes some total internal reflection. All right, let's move on. So number 5, this is a bit of a complicated one. The mark scheme was originally wrong. I'm not sure if it's just an error. Well, it must be an error. So a layer of liquid of refractive index 1.6 covers the horizontal flat surface of a glass block of refractive index 1.5. A ray strikes the boundary between them at an angle such that it travels along the boundary afterwards, so it's obviously at the critical angle. So then we need to decide which situation happened. So what we can do is, if I try and explain this, and so the underlying reason. So essentially you can have a glass block. So that had refractive index of 1.5. Then we had a thin layer of water, or some liquid. Water's actually about 1.3, so it's definitely not liquid. Not water, sorry. Yeah, that worked well. Let me try that again. Maybe if I exaggerate it a little bit. Yep, that went really well. One more. Yeah, I suppose that'll do. Or maybe if I just stop trying to be neat. There we go, let's say that's a liquid. So it's got a refractive index of 1.6. So then which way can it possibly go? Because that might be a bit confusing. Let's think back to the equation. So, the refractive index, or the critical angle, so sine theta c is equal to n2 over n1. And, well, to do inverse sine of a number, the number has to be between, if you think back to maths or GCSE, like, top level, the sine graph only goes between 1 and minus 1. So you can only do inverse sine of a number that is, between minus 1 and 1. Well, less than 1. If you do... So essentially what I'm saying is that n2 must be less than n1. Otherwise you end up with a number greater than 1. And if you try it, you just get a math error. So that doesn't work. So n2 must be less than n1, or physically the total internal reflection cannot occur. So in which scenario is n2 less than n1? So essentially what must happen is that the light must travel from the liquid to the glass. So I guess kind of like this, and then refract across the boundary. The reason it must do that is because in this situation, the liquid would be M1 and the glass would be N2. So this would satisfy the condition that N2 must be less than M1, and then we just need to find the critical angle. So the critical angle would be the inverse sine of N2 over M1. So inverse sine of N2, which is 1.5, and the first refractive index, which is 1.6. And then if we calculate that, we get 69.6 degrees, which approximates to 70 degrees. So it's travelling in the liquid at an angle of 70 degrees. So if we go back to the question, travels in the liquid at an angle of 70 degrees to the boundary. Which would be C, however, because I don't know what word I can use to describe myself without making myself feel too bad. Not very good at English, maybe. I'll have to put all this in the comments. Basically, on C, yeah, it is 70 degrees to the boundary. It's 70 degrees from the normal. That's the critical angle of 70 degrees, which is 20 degrees from the boundary. Wow, that's actually a great question. I do really like that. So the answer is D, the mark scheme was right. So I'll put that in a comment anyway. Hopefully you've already realised that. If not, surprise, surprise, same as me. Yeah, brilliant question actually. I like that a lot more than I did. So let's look at number 6 then. So number 6 is pretty straightforward. Monochromatic light may be characterised by its speed, frequency and wavelength. Which of the following quantities change when monochromatic light passes from air to glass? Well, the only thing that doesn't change is the frequency. So the frequency is always constant. So the other two, for wave speed is frequency times wavelength. Frequency is always the same. The only things that change are the wave speed and the wavelength. So B. So number 7, which of the following is correct when total internal reflection occurs? Light meets an optically less dense medium. So that's what we talked about on previous questions. So the sine theta c will equal n2 over m1. So n2 must be less than m1 for that equation to be valid, both mathematically and physically. So the light meets an optically less dense medium is definitely correct. Let's look at number 8. So this is a relatively straightforward question. What is the speed of light in glass? Refractive index 1.42. You can think of refractive index as like a measure of how much slower light is in that material. So if you've got a refractive index of 2, then the speed of light is 3 times 10 to the 8. Your speed of light will be in the material will be 3 times 10 to the 8 divided by 2. And it's the same for this one. So it's got a refractive index of 1.42. So we just do the speed of light and divide it by 1.42. And that gives you 2.11 times 10 to the 8 meters per second. So the answer is B. Right, let's look at the last one. So figures 1 and 2 each show a ray of light incident on the water-air boundary. So A, circle the letter below that corresponds to a direction in which a ray cannot occur. So cannot occur must be A. And the reason why is because, well, we've got this light. Let's change this colour. So we've got this light coming in and it's entering a less dense medium. So what should happen as you enter a less dense medium is that you refract away from the normal. So it basically should look, something like this. But it doesn't, it actually refracts towards the normal, so that's just completely wrong. So that's why A is correct. The second one says circle the letter below that corresponds to the direction of the faintest ray. Now, when you get refraction, which we have here, and that's in the correct direction. Try and get that a little bit straight. Well, that'll do. That's gone the correct way because that has gone into a less dense medium, it's gone into air, and it's refracted away from the normal. You will, however, get some, you always get some partial total internal reflection. It's normally a couple of percent of the, the intensity of the light. So you would get a really faint line that comes off in the direction of D. So the direction of the faintest ray would be D. Anyway, I hope you found that useful. If you liked it, give me a like. Yeah, and that's it. Hopefully it's helped. Thanks for watching. I'll speak to you soon.